Okay, so I think there'll be a fair bit of repetition in this, but I don't think that's necessarily a bad thing. This is, as that discussion has just highlighted, this is a complicated area and a lot of complicated concepts. And certainly myself, I don't really fully have my head around how the nested sampler works in detail. So it's definitely good to have Andrew's talk for mine on that. So um, generally, the theme of this talk is I'm going to go through some stuff you already seen before, actually just basic Bayesian inference, how that all works, how we do that for fitting, which applies, and then we'll move into the stuff you've seen before, parameter uncertainties, all this, and then move into the model selection as we get towards the end of the talk. So as always, I like to put my acknowledgements at the start because then make sure we thank the people that have been heavily involved in this work. Too many people to talk about, but yeah, these are all the people involved in the work that I'm going to be showing today. Okay, so although we're reflectometry scientists primarily here, this is a talk I've given, for general audiences as well. And so we fit many different things, high dimensional parametric modeling, complexity, all of this kind of stuff. And so what I'm showing today, although I'm going to be doing it in the context of PNR, it can be applied to any fitting problem, as Andrew showed earlier, with fitting just Gaussians, for example. And I have indeed used MCMC Bayesian for indeed inelastic, FMR, and of course PNR. So typically I give this kind of slide when I'm actually teaching this to students, but it just gives a bit of context to how the whole thing works. So I tend to ask my students, what does the error bar mean? And so, for example, we've got some quantity plus or minus some value. What does that value mean? And typically, I get a plethora of different answers coming out, and essentially the answer is whatever you want it to be, as long as you define it. So in this particular talk, I'm going to define it as a 1 sigma of a Gaussian, but it can be anything that you particularly want to find it. So that's something I just think is a useful point to mention. So the main point of this talk and what we do with the uncertainty analysis is essentially how do we determine this number from our fit? How do we actually give meaning to the parameters that we're actually pulling back from our fits? And this is a quote, and I don't know if I think Hawkins was actually in the audience. I don't know if you appreciate me saying this, but this is a quote I got from him. And he said that the best fit is the accident measurement. And I don't know if this is how he interpreted it, but this is how I interpret this particular quote, is that if you got the best possible fit on your data, where it went through all of the data points, not just the error bars, but the data points, so normalized chi-square of 0, that fit just happens to be where the data points landed within those error bars. And so therefore, to give meaning to that, we actually need to have the uncertainty value on top of that. Okay, so real basics, what do we get out of Bayesian uncertainty analysis? Well, we get the parameter and model uncertainties, i.e. the error bar. So you get your mean in this particular case, or 1 sigma uncertainties. You can get that can then translate to your SLD uncertainties in our case. Can give us parameter correlations, so we can see if we can uniquely determine a parameter from a model, or if it's indeed correlated with another model. So I'm going to step this back a fair bit. I'm going to go through an explanation of how what the basic Bayesian inference is for a bimodal distribution. And I have shamelessly taken this from a good YouTube channel, 3 Blue 1 Brown, who do a far better explanation of this than I can do. So, feel free to check that out. So we've got a fictional character called Bob. We have some characteristics of them. We know they are shy and withdrawn, and we know that they are organized and like routine. So we're going to ask the question, what is more likely? Is Bob a physicist or is Bob a builder? I'm going to be highly stereotypical here for the purpose of this presentation. And my hypothesis is that fits. Bob is indeed a physicist. So in order to calculate the numbers, we're gonna crunch it through here. So this is essentially what I would call it's what I call a probability square. So when we sum up the whole thing, it's probability of one, definitely probable. So first things first, we need to account for in this how many people fit the hypothesis, i.e., of a total population, and the numbers are very exaggerated here, just to make the point. The total population of builders and physicists, how many are physicists, how many builders. So we're going to arbitrarily say 10% of the population are physicists, which is our hypothesis, and the not hypothesis, to use the terminology, is 90% of builders. So now we need to go through and locate everywhere where we see this characteristic. So here, this is the probability of the evidence given the hypothesis. So this is where our hypothesis and where this characteristic matches our hypothesis. But because for the inference, we actually need to see where it is everywhere, we actually need to do the same thing for the builders. So how many builders actually match this? So if we say 40% of physicists match this bill, and only 10% of builders match this bill, we get these two particular curves. So as probably sort of said earlier, this here is the likelihood. I'm not sure this is the correct term, but I'm going to call this the not likelihood. Okay. So now we can build up our posterior or our inference. So this is obviously the probability of the hypothesis given the evidence. So to get this first square here, we times our hypothesis by wherever we see it, in this case, the likelihood. And then we normalize that by dividing through by where we've seen it on this side and everywhere else where we see this. Okay, so it's basically you're taking this value here and dividing it through this one. We put in some numbers, we do the crunching, we find out it's actually about 30% probability that you will indeed that Bob is a physicist. So it's actually far more likely that Bob is indeed a builder. Just in this case, by sheer weight of numbers, there's just far more builders out there. So even though it's the smaller percentage fit this bill, there's far more. And this is, the say Bayesian inference, and then you more commonly might have seen it like this. And as we've talked about earlier, we have this evidence term, which is the Bob. So at this point, it's worth taking a looking and saying there's actually different levels of inference. So most of us, if we use Bayesian, whether it be, as you say, bumps, MC, whatever your favorite package of choice is, we're looking at this level where we're looking at the parameter of certainty. So we're looking at a model given some data, we're assuming that our model is the correct one when we pull out these parameters. Next level, which is what we're going to obviously talk a bit about tonight, and I'm going to continue talking about, is model selection. Here we're looking at which model best describes the data, and we take the most probable model parameter estimates once we've done them. There is another level, and I'm sure there's more to it than this. I'm not a statistician, and there is this thing called model averaging. And so this actually works by not fully discounting one model over the other. The issue, as we'll go into later with the way we're showing model selection, is that you're basically saying, well, it's that one. Although there is still some finite probability, it could be partially the other one. And so therefore, the way I understand this, and I'm by no means an expert, the model averaging actually gives you a way to potentially say, okay, I want to get parameter uncertainties which take both models into account. I personally have no experience of it, but I know it's there. So I just wanted to put it out there so you're aware that it exists, but I won't be talking about it tonight. Okay, so let's roll back. How do we do Bayesian inference in the fitting? How does this actually work, the nuts and bolts of it? So, we'll start with terminology. So our posterior, as we said earlier, our parameter uncertainties, correlations, all this kind of stuff. Our prior, effectively, for most of us, this is the fit ranges. Ultimately, I'll go into a little bit of that in a minute. Likelihood, how good the current fit is, or when you put your set of parameters in, how good a chi-squared, if you like, you get out of that. And finally, the evidence term, this is the total probability of seeing the evidence. So that can be used for our model selection. So a quick aside on priors, I'd just like to have a little bit of a health warning. In most cases, we use uniform priors. This is to say it's equal probability everywhere inside, but zero probability outside your fit ranges. And this is the thing to do if we're using what we call improper priors and we're not, we're kind of going, yeah, it's about that, but I have no external justification for this, but it's about that. You can use other distributions if you like. So, for example, if we've taken a TEM slice of our thin film and we've got, say, okay, we know the thickness of this layer is this plus or minus some error, we could put that in as a Gaussian prior. And that's a proper prior because we have other evidence to support that. And so, therefore, that is a varying probability away from the mean. But you do have to have good justifications for using that because that is going to influence your final parameter uncertainties. And indeed, it would also influence quite heavily your evidence calculations later on for model selection. So how does this all work for fitting? Because what I've shown you earlier on is a bimodal distribution, but what we deal with is continuous. So we now have to update this equation. So now the hypothesis is now a parameter set given some model M. We've got the data D, given some parameter set and the model for the likelihood, and your evidence now is the data given some model. So essentially what we're doing here is we need to calculate a posterior value for ideally, for as many of these parameter sets or numbers, if you like, you're going to chuck into your model as possible to build up this posterior. Okay, so back to my probability square again. So we have some prior values. So we're just going to pick the peak of the Gaussians. That's very, very probable, if you like. And we're going to say, and then we also have to cover everywhere where we haven't picked. And then once again, where do we see that it fits the data? So basically, how well does it fit the data, i.e. our likelihood? And then we need to go around the rest of the prior and see how well does that particular set of numbers match. Yeah. And so then you do this for each particular point and you go around and you keep crunching the data to get each part of the posterior. But you might notice that this bit is very tricky because if you've got to calculate all of these values every time you want to calculate each part of your posterior distribution, it's going to be very time consuming, very costly. So I'm going to do a very quick aside here. Since it was mentioned, I feel like we'll just reiterate it again. I haven't got the slide in here at the moment. MCMC typically gets around this by assuming that you are converged. So what the MCMC does is you can imagine it has this equation here of where you currently sit. It has the same one of the proposal, and it divides one by the other because it assumes that you're at a point where the fit is not getting better. And because of that, you literally divide out the evidence term. So that's the thing that the MCMC does, is a bit of a shortcut around it to get around this. But if we want to do model selection, we actually need this value. So as Andrew has shown earlier, in order to calculate this, we have to use something like a nested sampler, such as UltraNest, Dynasty, Multinest, so on and so forth. This is computationally expensive, though. Okay, just going to put that out there. So hopefully most of you are very familiar with this. We are basically, we have a standard kind of fitting procedure. We try and fit some kind of base model, which is based on our prior belief. So in high condensed matter, quite often, our model 0 is the sample structure the growers told us they grew. We then try various models of increasing complexity to fit the data. We compare them based on goodness of fit or the model complexity, number of parameters. And whilst I appreciate this isn't always the criterion for some of you in the room, for us, typically, we go for the simplest one is ultimately probably the right one, so Occam's razor. So then the caveats are here, what happens if we've got many models of similar goodness of fit? Is the best fit values we've got unique, or are there many parameter sets that also fit the data? Our first phase problem. So let's start with, so what I'm going to say here is that we're going to show a couple of case studies. Now, this is more leaning towards the parameter uncertainty side. And the reason why I'm showing this is actually, although what I'm showing here could be done with an MCMC, this is actually done, in fact, with nested sampler. And this is what popped out. As Andrew Nelson's already said, nested samplers are very good at pulling out multimodality just because of the way they do these contours of likelihood. The issue with the MCMC is it'll tend to have walkers that walk around, and you're hoping that they happen upon these kind of likelihood peaks in the prior volume, if you like. And the only way really to do that with an MCMC is to have large populations, big global initializers to kind of get that. Nested sampler is more efficient. So this is kind of an example where you can get that out. So this particular case study was nickel graphene. So the thing here was trying to identify if there was magnetism in the graphene induced proximately from the nickel. And you can see all our correlation plots. We've got two probability, two options here. So now we've got this, we need to do something with it. So this is where we actually go to other information to see, can we knock out one of these peaks? So they did Raman spectroscopy on the layer, and that told us that they can only possibly have 2 or 3 monolayers of graphene on the surface. So that means we can now go back and reset our priors, tighten them up, and actually just knock out this other mode. So what that means, if we look at our graphene thickness, well, that means we have to go to the thin end of our graphene thickness. So we get rid of this correlation here. That happens to then, if we track that across, we should be able to knock out another correlation. So now we can knock out this one of the graphene interface. And finally, that means we can knock out this one of the nickel surface interface. This is kind of like just a good lesson that obviously with the posteriors, you do need to treat them carefully, because if you'd have just gone on pure probability alone and not used other information, you'd have probably gone for the other one. So it's about bringing everything in together. But what we're showing is by using these techniques, it gives us additional information to then ask the question of actually, yeah, we should be going looking a bit more here rather than just treating the numbers that come out of fit. So next case study, this is going to be where I get into the model selection side of things. So there's material, cobalt, zinc. I'm not going to go into too much detail because, to be honest, I'm not an expert in schemamic materials. But ultimately, what we were interested in was we did temperature and field dependent measurements, and we were trying to find out where in this well, first things first, was there a helix at all? Was there a helical phase? And secondly, if there was, when did it go to a uniform magnetization? And so you can see how this is setting up the model selection problem. So to start off with, the helical model, we basically followed this kind of double sinusoid type, double helix type thing, already used in a prior paper. And it gives you a kind of shape, kind of like this. It's not an ideal SLD, of course, but approximation nonetheless. And this gives you an idea of some of the data. I like to do a bit of an aside here because it was quite interesting when we took this. And this here is the lowest field data that we measured at. And we looked at, again, as you do when you first do your MCMC, look at your posterior distributions. And we got correlations like this. And so essentially what this is telling us is that we're looking for a particular, to see if the helix has a particular wavelength. And what we saw that whilst, as you'll see later from the evidence, the helix fitted this data better than the uniform magnetization, it couldn't lock down on a particular value of the wavelength. And so there's potentially two reasons for this that I can think of. There's a scientific one, and then there's like an information one, and it's probably a bit of both. So the scientific one is potentially that there wasn't enough field to stabilize a particular wavelength of helix. Or the information argument is because we're at low field, the splitting is less. And so because the splitting is less, there's less information about the magnetism in the data. You can see the error bars are reasonably large here. We have to count very quickly for these measurements. And so perhaps that's maybe more the reason why it couldn't pin it down. We up the field slightly, and all of a sudden, okay, we've got still a little bit of correlations going on, but now the values are nicely tight. And actually, we can see what we actually have a specific value coming out for the wavelength of the helix. So I just thought that was, again, a nice way we can use and look at the correlations and the posteriors to actually give us a little bit more about the information in the data, what's going on, are we over-interpreting? So here's an example of going through the helix versus uniform magnetization. So this is uniform magnetization we've got of that 10 milliliters, that nicer correlation data set. So a fairly standard profile. And here's our kind of helical profile. Helical profile fits the data significantly better than the uniform. So at this point, probably don't need a nested sampler, but it's good to have that as a backup. So if I plot, we did this for a number of fields. So I've done log field on the bottom here, and then reduced chi-squared, which is your traditional way of going about it. You can see that the helical model in orange crosses over roughly, this is about 40 millitesla, and then it becomes more better fit, shall we say, with the uniform model. But remember back to that quote, the issue with these are our best fits. Are there other fits? How much variation have we got in those fits of that posterior that actually play into this? We're only looking at one particular point. So what we need is something that's going to give us that scope of that entire prior volume to tell us actually, yeah, the one model is more likely than the other. So what we've got before, now we ran the nested sampler on all of these. Okay, now I have inverted this here. So this lower is towards the bottom of the figure is better. And I've done this simply so that it matches the same shape on the other side. So it's easier to compare. And it does indeed actually follow the trends that we got here. But there's a couple of key points that are quite interesting. So if we zoom in here, if we look at the chi-squared line, these look fairly well separated, these two models, and you go, yeah, I'm confident that that is indeed helical. Not so much the case when we then look at the evidence. So if we zoom in, you can see the error bars are not quite, but they're within a couple of sigma of each other, of overlapping. Okay, let's go and do the same thing again with another part of the data set. You might have noticed this outlier earlier on. We think this was just a not so perhaps well counted out measurement, which is why this isn't so well separated, but it provides an interesting thing to look at. Once again, here you would say, oh, these two are fairly well overlapped, but actually, when we look at the model evidence, they are miles apart. So what's going on? My understanding of it is this. The helical magnetism has many, many, many more options of how to fit the data in the way it's going. So therefore, that likelihood peak, if you can imagine in your prior volume, if you have a nice peak of where you think all of the available, best fits are, is smeared out more in the helix than the uniform magnetization. Uniform magnetization has a lot less options. So what that means is, because the helical can do all sorts of other things, it has to fit the data a lot better to justify its additional complexity of the model. And by complexity, I mean of what it can do to the SLD in our case, not just the number of parameters. That's something that's, it's freedom, if you like, and that's an important thing to bear in mind. So Occam's razor, ultimately, whether you like it or not, is built into the evidence calculation, which for us is good because you can think about how much information is in the data. Are we over-interpreting that information? So Andrew Nelson covered these earlier. I'm going to cover it very briefly again. So what we can do is, rather than just look at it on a graph lab, we can actually do Bayes factors. So essentially, we're taking the ratio of one model evidence over the other. Now, typically, we're basically taking the odds. So we're looking at the posterior odds, which is your Bayes factor, times by the prior odds. Typically, if you've got no other reason, you basically make the prior odds even, because you basically say, I don't have any preconceptions of which model I think is more probable. So we just basically knock that term out, and then we just use the Bayes factor. And so again, another scale like you saw with Andrew Nelson. So this is primarily these scales. There's many different ones, and there's different people who've normalized them to different things. I'm going to show the Jeffreys scale here, which was essentially determined on betting odds, if you really want to know where it came from. And just to give you an idea of what that Bayes factor actually means in some way, shape, or form. So if it's less than 1, it's inconclusive. So what you'll see later on is I've only shown you the Bayes factors which are positive. So at some point I've swapped which way around I'm dividing one by the other when it becomes less than 0, because you can't say anything, but you can say anything when the ratio is higher. As it gets higher and higher, it becomes very strong evidence, and you can convert this to some form of probability value as well. So similar figure to what I've shown before, but now I've got your log Bayes factor on this side, we've got field on this side, and I've put in some effectively probability isotherms, for want of a better way of putting it, of various sigma. So you can understand what this means. So I do apologize, I've swapped the colors around here. This was a mistake a while ago, but anyway. So these blue ones are the helix, orange ones are uniform. And for the most part, it's really stonkingly strong that we're either in a helical state or we're in the uniform magnetized state. But again, at that crossover point that I showed you earlier, not so clear. So now this is a bit above a sigma of 2, but below sigma of 3-ish. So it's not totally clear. And you can envisage that if we were to do this for all the isotherms, you could start to build up a phase diagram of where indeed it actually crosses over. And this is actually then really becomes really useful and really powerful, because now we've got a method that takes into account the whole prior volume, the whole model, given the data, and not just a best fit of what's going on. So obviously we should talk about the pitfalls. As I said earlier, it's computationally expensive. Nested samplers take a while to run and they use a lot of process power. Okay. Your final result depends on your parameter priors. And this can skew your results. So, and this is the same with when you're doing parameter uncertainties as well, but it's particularly acute when you're comparing models. So for example, take for a reflectivity curve, the intensity, where we're fitting the I naught for whatever reason. That is a nuisance parameter, and you can basically lock it down fairly tightly, and you really want to keep that range. And if for the same data set, there's no reason why that range should be different between models for the same data set. And if you do, and you make one really big and one really tight, you're again smearing out that likelihood over a big prior volume. That lowers the value. You can think of it as in entropy terms as well, where entropy is from prior to posterior, and you're skewing it again. So really, if you're going to do this work, I would really say you keep apart from the thing that defines the model, you keep all of your priors identical to one model to the other, and then you can remove this as a concern. It doesn't account for how physical your models are. All right, you can put anything into it and it's going to give you some number, but you still need to sit down and go, well, actually, is that physically possible? Let's go back to the graphene example. There was one of the options it gave us was too thick. Our priors were too big. So we needed to go back and tweak that. And as I kind of hinted at earlier, your Bayes factors only select one model over the other. That other model may still have some probability of being useful, being correct. So do bear that in mind. So I was asked also to add in a bit of a comparison for MCMC nested sampler. I'm going to do my best, but I'm certainly not an expert here. So in both of them, as we said earlier, you can gain the posteriors from both. You get parameter uncertainty, you get correlations. I put this one in here. So one of the issues we have is, especially with MCMC, is this autocorrelation lag thing. So if you need to get independent samples to make the posterior correct. And so the way you can increase that typically with MCMC is we just increase the length of a Markov chain. And nested sample, you increase the number of live points. When I've used UltraNest, it adaptively does that it basically goes through the whole thing and says, "Oh, I haven't got enough independent samples," and goes back over the posterior with more and more live points until it has. The two ways of doing kind of essentially a similar thing. Multimodal posterior, so I talked about this. MCMC can do it, but it's hard work. It's not efficient. Nested sample, it kind of comes out of the box because of the way it works. Convergence time, if you're just trying to fit your data, MCMC is going to beat it every single time because it's just a far more efficient way of doing things. But if you need that model evidence, to be honest, nested sampler is the way to go. So hopefully, I've convinced you, if you weren't already, that we can get quite a bit out of using Bayesian analysis for our parameter uncertainties, correlations, give us information about multimodal models, and if we're indeed overfitting. And then also, getting parameter distributions as well is very useful as well, i.e., are they Gaussian or not? Something I didn't really cover too much. Model evidence we can use to compare models. Again, we can use it to look for overfitting, overparameterization. And I know we're reflectometry kind of meeting here, but remember that we can use this for all types of areas. It's not just for reflectometry. So yeah, hopefully that was useful.